This is Invention Chronicles. We live in a world that craves energy. Our cities glow brightly through the night. Our homes are filled with devices that hum and whir with electricity. This constant demand for power has pushed us to find cleaner, more sustainable sources. Solar panels have become a familiar sight, dotting rooftops sprawling across vast fields. They are silent soldiers in our fight for a greener planet. They capture the sun's abundant energy and transform it directly into the electricity that fuels our modern lives. The principle is simple and elegant, a true marvel of engineering that has already changed our world for the better. But these silent soldiers have their limits. Solar panels are big. They are heavy. Their rigid, flat surfaces require specific conditions to be truly effective. You need a strong roof that faces the right direction, or a large open piece of land that is not being used for anything else. The cost of manufacturing and installing these bulky units can be a significant barrier for many families and communities. Look around any major city. You will see towering skyscrapers with massive walls, but relatively small roofs. These vertical giants consume enormous amounts of power. The very structures that define our urban landscapes, tall office buildings, the apartment complexes, the winding overpasses, are mostly passive surfaces. They stand strong against the wind and rain, but they do little more than bake in the sun. We are surrounded by billions of square feet of wasted real estate, surfaces that are bathed in sunlight every single day but contribute nothing to our energy needs. This is the great challenge we face. How do we turn our entire built environment into an active part of the energy solution? What if we could rethink what a solar collector looks like? What if it did not have to be a heavy, rigid panel? What if it could be as simple, as flexible, and as versatile as a coat of paint? Imagine a technology that could be brushed onto a wall, sprayed onto the roof of a car, or rolled onto a curved, unconventional surface. This is not science fiction. This is the promise of a remarkable breakthrough that could fundamentally change our relationship with the sun. A new idea called solar paint is emerging from laboratories around the world, and it could help us capture energy in places we never thought possible. The breakthrough is as elegant as it is revolutionary. Solar paint. It looks and acts just like the paint you might buy at a hardware store. It comes in a can. You can apply it with a brush or a sprayer. But this is no ordinary coating. Mixed within its liquid base is a collection of extraordinary microscopic particles designed to capture sunlight and convert it into electrical energy. When you paint a surface with this material, you are not just giving it a new color. You are turning that surface into an active, power-generating solar collector. The wall of a house, the roof of a bus, the surface of a laptop could all become sources of clean electricity. Think of it like this. A traditional solar panel is like a single, large, carefully crafted window for catching light. Solar paint, on the other hand, is like covering a surface with millions of tiny, microscopic windows. Each particle in the paint is a miniature solar cell. While one particle alone does very little, billions of them working together across a large area can generate a significant amount of power. This distributed approach is what makes the technology so flexible. It does not demand a perfect, flat, south-facing installation. It simply works wherever the sun shines, transforming passive surfaces into a vast, interconnected network of mini power plants. This technology relies on some of the most advanced materials ever created. Scientists have developed what are known as quantum dots. These are semiconductor crystals so small that they are only a few atoms across. Their tiny size gives them unique properties, allowing them to be tuned to absorb specific colors or wavelengths of light. By mixing different sizes of quantum dots into the paint, scientists can create a formula that captures a much broader spectrum of sunlight than some conventional solar cells. This means more of the sun's energy, from visible light to invisible infrared, can be harnessed and put to work generating electricity for our use. Alongside these quantum dots are other nanomaterials that serve critical functions. Some act as a conductive grid, forming a microscopic highway system within the paint to collect the electrons that the quantum dots release. Imagine tiny wires, far too small to see, that are mixed right into the liquid. When the sun's energy knocks an electron loose, these pathways guide it, creating an electrical current. Other nanomaterials might help the paint stick to different surfaces, or protect the delicate quantum dots from moisture and air, ensuring the coating can withstand the elements and continue producing power for years, just like a good quality exterior paint should. Well, it's pretty neat. To truly understand how solar paint works, we need to zoom in. Way in. We need to look past the painted surface and into the microscopic universe within the coating itself. Here, in a world measured in nanometers, the real magic happens. The key players, as we have learned, are the quantum dots. These are not just tiny specks. They are precision-engineered crystals. The amazing thing about a quantum dot is that its size directly determines what color of light it absorbs. A larger dot might absorb red light, while a slightly smaller one absorbs blue light. It is like having a set of miniature color-coded tuning forks for sunlight. This tunability is a huge advantage. The sun emits a wide spectrum of light, and traditional solar panels can struggle to capture all of it efficiently. By creating a paint that is a cocktail of different-sized quantum dots, scientists can design a surface that is hungry for almost the entire solar spectrum. It is like setting out a full buffet to catch every last ray of energy the sun sends our way. This is a big step up from being limited to just 1 or 2 dishes from the solar menu. This is what gives solar paint the potential to be surprisingly effective, even if its initial efficiency numbers seem lower than traditional panels. So, what happens when sunlight strikes one of these quantum dots? A particle of light, called a photon, strikes the quantum dot. If the photon has the right amount of energy, which is determined by its color, the quantum dot absorbs it. This jolt of energy is enough to knock an electron loose from its atom inside the crystal. This newly freed electron is now full of energy and ready to move. But a free electron is not enough. You need to give it somewhere to go. This is where the paint's other ingredients come into play, creating a complete electrical circuit. This is the job of the conductive nanomaterials, such as tiny nanotubes or graphene flakes mixed into the paint. They form an invisible, interconnected web throughout the coating. When an electron is freed by a quantum dot, this web acts like a system of roads, guiding the electron away. Billions of electrons, all flowing in the same direction through this network, create a steady electrical current. This current is then collected by a transparent conductive layer, applied over the paint and channeled into wires. From there, the electricity can be used immediately to power a device, stored in a battery for later, or sent into the building's main electrical system. Yeah. An idea as revolutionary as solar paint cannot stay in the realm of theory. It must be tested, measured, and proven in the real world. That journey begins on the lab bench. Scientists in labs worldwide test formulas. They paint small squares with their latest batch of solar paint. Glass metal plastic samples are placed under solar simulators, lamps mimicking sunlight. Wires connect samples to sensitive meters and multimeters. Close up, painted metal sheet under lamp with wires to meter, marketing visual. Tests are rigorous and revealing. Different types of quantum dots, new conductive materials adjusting paint thickness, every change documented and analyzed on computers and notebooks. The key metric is efficiency, percent of light converted to electricity. Early versions had very low efficiency. 2018 University of Toronto study, colloidal quantum dots improve performance. It's a slow, incremental process of refinement. The proof is in the numbers, graphs, and charts. Solar paint efficiency rising but below high-end silicon panels. Researchers now demonstrating efficiencies entering the double digits. Efficiency isn't everything. Solar paint offers scale and versatility. Rooftop panels cover limited area. Painted walls could cover entire buildings. Pilot projects move testing from lab to field. Test patches applied to buildings. Rain-wind temperature swings. Experimental vehicles coded to measure added range from painted roof and hood. Field trials test durability and the systems to collect and use the power. Each successful test builds confidence and moves us closer to a painted solar future. The potential benefits of solar paint are immense, promising to weave energy generation into the very fabric of our cities. Its most obvious advantage is its versatility. Because it can be applied to almost any surface, regardless of shape or size, it opens up vast new areas for solar collection. The walls of skyscrapers, the curved roofs of stadiums, the surfaces of electric vehicles, and even noise barriers along highways could all be transformed into power-generating assets. This could dramatically increase a city's ability to produce its own clean energy, reducing reliance on distant power plants and making the grid more resilient and stable. Furthermore, solar paint could be significantly cheaper and easier to install than traditional panels. The manufacturing process for the paint's core components is being designed for large-scale production, which should drive down costs. The application process itself is far less labor-intensive than mounting heavy, rigid panels. There is no need for complex racking systems or structural reinforcements. For an existing building, a new coat of solar paint could be applied during routine maintenance, seamlessly integrating renewable energy generation with minimal disruption and cost. This accessibility could democratize solar power, making it available to a much wider range of buildings and owners. However, we must also be realistic about the challenges that remain. The primary hurdle today is still efficiency. While improving, solar paint currently converts a smaller fraction of sunlight into electricity compared to conventional silicon panels. This means you need a larger painted area to generate the same amount of power. Another major concern is durability. A painted surface is exposed to harsh weather, UV radiation, and physical abrasion. The delicate nanomaterials within the paint must be robust enough to last for a decade or more to make the investment worthwhile. Scientists are actively working on protective topcoats and more resilient formulas to address this very issue. Beyond the technical challenges, there are also practical and environmental questions to consider. The large-scale manufacturing of quantum dots and other nanoparticles must be done safely and sustainably. We need to ensure that no harmful materials are released into the environment during production or at the end of the product's life. As with any new technology, clear standards and regulations will be needed to ensure safety, quality, and proper disposal. Building trust with the public and with regulators will require transparent, long-term studies that prove both the effectiveness and the safety of this groundbreaking technology across its entire life cycle. Solar paint is not going to replace every solar panel overnight. Instead, it should be seen as a powerful new tool in our clean energy toolbox. A person rolling solar paint onto a small section of their wall with a simple wiring kit ready to be connected. In the near future, we will likely see a hybrid approach. Buildings might use high-efficiency traditional panels on their ideal, sun-drenched roofs, while using solar paint to capture additional energy from their vast wall surfaces. Electric vehicles could use the paint to supplement their battery charge, slightly extending their range, or powering auxiliary systems like air conditioning. It is about adding energy generation everywhere we can, complementing existing technologies rather than competing with them directly. The path to widespread adoption requires a few clear next steps. First, research and development must continue to focus on boosting efficiency and improving long-term durability. This is the foundation upon which everything else will be built. Second, pilot programs need to be scaled up. We need more buildings, in more climates, testing the technology and providing real-world data on performance and longevity. This will help refine the product and demonstrate its value to architects, builders, and city planners. These visible examples are the best way to build confidence and generate market demand. finally, industry and governments must work together to create a clear pathway to market. Thank you for watching, stay curious, and keep exploring the world of invention and discovery.